Okay, let's start with concepts of motion in chapter 1. So we can describe several types of motion. We have what is called linear motion. There is also circular motion, projectile motion, and rotational motion. Let's start off by looking briefly at linear motion. This is motion along a straight line. And we will talk a little bit more about linear motion as we go along, but we're just defining our types of motion now. Then we have circular motion. This is motion along a circular path, or you can say motion in a circular path. There is also projectile motion. This is a two-dimensional motion. We will talk a little more about projectile motion as we go along. So this is a two-dimensional motion of an object that is thrown through the air. Then we have rotational motion. This refers to the rotation of a solid object about a fixed axis. We can show these types of motion on a motion diagram. So what do we call a motion diagram? We'll do that next. So a motion diagram will be something that looks like a video frames. So we can say a motion diagram is like video frames, where we can look at the motion of an object frame by frame, if you like. So let's take an object in linear motion, for example. Or first of all, let's start with stationary object. So consider a ball at rest below. So I draw a diagram like that with a ball at rest. Okay. So with this ball at rest, each time you look at a ball, it will just look the same. The motion will be in the same place. So let's say this is frame 1. In frame 2, you draw a diagram again, the ball will still be in the same place. In frame 3, the ball is in the same place. So this is ball at rest. Let's look at an object in linear motion. So in linear motion, we expect the object's position from frame to frame. So let's take a look. So let's consider the ball again, but this time it is in linear motion. So you take a ball first in frame 1. So this is your ball. And in frame 2, you do the same thing, but this time the ball is here. In frame 3, the ball will be here. And in frame 4, the ball is here. So this will be an example of an object in linear motion. So the object looks, its motion is changing uniformly or over a constant interval in time. If an object is speeding up or slowing down, then we say its motion is non-linear. Let's consider examples of an object speeding up. So let's look first at the motion diagram of an object speeding up. So in the first frame, this is what it will look like. So first frame, this is the object. This is frame 1. Frame 2, the object is here. Frame 3, the object is here. Frame 4, you can think of the object this way. Frame 5, the object here. And let's take a frame 6, object somewhere here. So putting it all together, speeding up. So putting it all together, we see an object speeding up. This is an example of non-linear motion. So I draw this here. Object starts off initially. Intervals are smaller and they get larger as the object speeds up. So this is an example of speeding up. The opposite would be an example of slowing down. Let's look at the motion diagram for an object slowing down. This time I will just draw the completed motion diagram. So here is the diagram again, this time for an object slowing down. So the object starts off, the intervals are larger as you can see, and then they get smaller as the object slows down. So this is an example of an object slowing down. Intervals start large and then get closer together, and then are closer together at the end until the object comes to a stop. Then looking at projectile motion next. So suppose we have an object that is thrown into the air. Let's consider again our ball. Let's imagine that the ball is thrown into a basketball hoop. So an example of projectile motion will look the following way. So we throw this object. The intervals initially are larger as it's going up, and it goes into the hoop. So this is an example of projectile motion. We'll do more on this later. As I mentioned, this is a two-dimensional motion. So we shall look at the horizontal dimension and the vertical dimension separately when we come to it. So let's go to the next section, which is the particle model. So far, as you have seen, I've been using a ball to represent the motion, the object that is in motion. It is more convenient to go to a so-called particle model so that instead of drawing a ball or a vehicle or a human stick figure running around or a car driving around, I can just use a point or a particle representing this object which is in motion. So that's the idea of a particle model. So let's look at that next. So we can say that in the particle model, instead of drawing objects like balls, cars, or human figures, we shall represent these as particles. And by using a particle, this means that we shall draw the object as a point. So for example, for linear motion, so this time, instead of drawing the balls, I'll just draw an object in linear motion, and I'll show that its position changes uniformly over time. So this is an example of linear motion with a particle model. For nonlinear motion, where the object is speeding up, I can draw an example. I can draw something like that. So this is nonlinear motion where the object is speeding up. And then I'll draw nonlinear motion where the object is slowing down. So this is nonlinear motion. This is slowing down. So in order to use the particle model to actually do any work, we need to first define what each of those points mean in space. So we shall define what is called position and time for the object. If we look at the motion of an object, it would be useful if we knew where the object was at any point in time, meaning if we knew the position of an object in time. Position can be made on a coordinate system. So in order to know the object's position, we need to identify a coordinate system. And we can use a Cartesian coordinate system, which we call our XY coordinate system. So to know where an object is in space and when it is there, we need to know its position in space and time. We use the typical Cartesian coordinate system. So an object's position in the Cartesian system can be represented by a pair of letters X and Y. So we can represent an object's position by a coordinate in the Cartesian coordinate system, which is given by two letters X and Y. So for example, if we have an XY coordinate system, this is X and this is Y, with numbers 1, 2, 3, and 4. This is 1, 2, and 3. An object at position 2, 2 will be given by 2 and 2, by the coordinates 2 and 2. So we can say position where objects, so we can say in this coordinate system, an object is 2 units from X. In this coordinate system, an object is 2 units from the origin along X and 2 units from the origin along Y. The object's position is given by the coordinate 2, 2. So the object is at position 2 from X and position 2 from Y. So that's the coordinate 2, 2, which is X and Y. Another way to locate the object is to draw an arrow from the origin to the point representing the object. This arrow is called a position vector. So we can represent that again on the coordinate system, the Cartesian system. So the object is at this position, which we originally called position 2, 2. And this is the position vector for this object. We can call the position vector, we can label the position vector as vector r. So now that we know what a position vector is, we can go to the next quantity that we can use to identify an object's motion, and that is called displacement. So let's say that now that we have identified, or at least now that we have defined a position vector, we can define displacement. We define displacement as a change in position of an object. To illustrate this on a graph, let's consider the graph below. Suppose an object starts from the following position. Let's call it position A. Suppose an object starts from position A and ends up at position B. We can represent each of these positions by a position vector. This is position vector R1, and this is position vector R2. So the object goes from position A to position B. So the displacement of the object is this vector here, delta R. So we can say that when an object goes from position A to position B, we can find its displacement delta R, which is what we define as displacement. Displacement is a change in position. Let's call this Y, and that's X. And these are position vectors, so this is a vector notation. So if you look at the object's motion, it goes from R1 plus delta R and ends up at R2. So we can say that delta R, which is the displacement of the object, is equal to R2 minus R1. This can be interpreted to mean that R2 is final position and R1 is initial position. So displacement delta R is final position minus initial position. So we can now write delta R to be equal to R final minus R initial, where the subscript F means final and the subscript I means initial. Okay, so our displacement is final position minus initial position. Displacement is a vector quantity, as we can see. This means it has both magnitude and direction. We will discuss more about what vectors mean and what magnitude and direction mean. But for now, we need to just remember that displacement is the final position minus the initial position. And using the position vector notation means that the displacement vector is independent of the coordinate system that we use. So let me put that as a note. That's an important point to remember, that the coordinate system, the displacement is independent of the coordinate system. Now that we know what displacement is, we can look next at velocity.